Are you a Raspberry Pi builder who wants to make your projects easier for others to reproduce? I'm going to show you how. The existing methods for sharing firmware are hard. The first method you might consider is building an image, ripping it, and hosting it somewhere on the internet. The problem with this approach is that you can't make any mistakes during your build process. The second problem with this approach is hosting and delivering large firmware files. Usually, these files are larger than 2 gigs, which can be a deal breaker for people on slow internet connections. You could publish a tutorial with step by step commands that others will have to execute. This approach is fragile because your readers will make mistakes. Your documentation goes stale the moment you publish it. And as time goes on, your readers will experience unexplained errors as Linux changes and the commands in your tutorial go stale. Tutorials are fragile for a lot of the same reasons that manual firmware creation is fragile. You could go the route of projects like the Pi-hole or Umbrel and publish installation scripts. Shell scripts are not easy for neophytes to consume, and installation shell scripts demand way too much trust from your users. Finally, there's Buildroot and Yocto. These are full-blown firmware development tools used by IoT builders, and they're also notoriously difficult for new users. Not many Linux builders are excited to use these tools. Yocto and Buildroot are hard. Their complexity limits your community of potential collaborators. A better solution makes it easy for others to reproduce your builds. It should be transparent about what software is being installed. It should be accessible for less experienced Linux builders. It should enable collaboration through small files that are easy to download and easy to understand. So let's go over how my process works. Here's my build environment. I have a home Wi-Fi network, and there are 2 devices, a Mac for development, but you could also use a Windows or a Linux system, and a single board computer, in my case, a Raspberry Pi. The Pi is running a clean, up-to-date version of Raspbian, and we're going to automate the installation of software on the Pi so that others can reproduce my projects. To automate the reproduction of a project, we'll be running 2 containers on my dev workstation. One container will be running Ansible, and our second container will be running AppCacher NG. The Ansible container is where we spend most of our time. This container is used to execute Ansible playbooks. The playbooks install software on our target system in a controlled fashion with minimal steps for the user. The AppCacher NG container is used to save developer time. We eliminate redundant downloads of large files from the internet by saving a copy of packages to the local caching server. This dramatically reduces build time for solutions that depend on repositories for components. So once we've tuned our containers and set up our target Pi, we validate our connectivity from the Ansible container to the Pi using a simple ping command. Next, we copy an SSH key to the destination system so that we can use Ansible to deploy software to the target. And finally, we can deploy a playbook to the target system. Ansible playbooks can be used to orchestrate changes on our target system. We can use Ansible to install software using apt-get. We could compile software on the target system using GCC. We can modify and copy configuration files over to the target system. Our Ansible container launches a playbook, and then it will run the commands in that playbook in a controlled, repeatable order against the target system. When a playbook includes commands for installing Vim, it will reach out to my caching server and request the package. It's our first time running the playbook, so the caching server won't have Vim, and the caching server will request Vim from the Raspbian repositories. It'll pull down a local copy of Vim from the official Raspbian repository, and finally vend Vim to our Pi. If we had a bug in our playbook that forced us to rerun the process, we don't have to wait for a slow internet connection anymore. The caching server now has an up-to-date copy of Vim, and now we're really hustling, no more waiting for long, redundant internet downloads. This approach makes it easy for others to reproduce your builds. Ansible playbooks are easy to inspect. You can review the order of installation commands by looking at the roles system tasks main.yaml file. The main.yaml file can be used to break my software installation into components. And so you can see in this build, I have 7 major sections of software installation commands. This makes it easy for me to reuse components across projects. You can see I've got host APD stuff and DNS mask and light HTTP. If we look at the essential YAML, which is the first file on the list, we'll see that I slurp some information from the remote system. And I can use this to add debug statements to a playbook that would prevent it from being installed on an incompatible target. In my essential script, I tune the device to use my app cacher ng server for its local repository, and I do a bunch of housekeeping to prevent tedious bugs during the build process. A more interesting example is to look at one of my host APD YAML files. This tunes the target system to become a Wi-Fi access point. And you can review the installation commands and configuration files so you know exactly what I'm doing in this build. This makes collaboration and iteration easy. My fellow builders can propose fixes through Git pull requests. For next steps, you should experiment with other playbooks, publish your own, and automate your SBC project creation. I've got some example projects here. My first one is a captive portal community hotspot. It runs a anonymous image board where people can upload and download pictures and put text in. It's very much like the Pirate Box, if you're familiar with that project. I've also got a cool Wi-Fi cybersecurity practice lab. I use this to introduce cybersecurity to kids. They can practice hacking the Wi-Fi network. They can crack a Wi-Fi password, find a vulnerability on it, get shell access to the Pi, and then be able to go and look at the log files and see the evidence of their attacks. So they also get an opportunity to practice defense, and they can change the build so that it is more secure and resilient to the attacks that they wielded against the asset. And then I've also got a builder hotspot, which is basically this project without Docker containers. So if you have challenges with your home network and you don't really like Docker, you can just rip this firmware to a Raspberry Pi, and then you just need a second Pi to push your builds against. So if you need help, there are 4 great ways to get a hold of me. Send me an email at p@mechanabanana.com. You can reach out to me at Twitter at Patrick McCanna. I'm also a recent Noster user. But the most scalable way is to file issues on my GitHub page for the firmware builder containers. This is the most scalable way. Any issues that you post here force me to update my documentation and my code. If you do check out this project, please reach out to me. Let me know how it worked for you. If you publish any of your projects, tell me so I can tell others about your cool projects. I am really excited about this. I love using this for prototyping. I hope this is valuable for you. I really see this as a much easier way to introduce new folks into the exciting world of IoT development. Thanks for checking this out. Please reach out. Let me know how it goes. Cheers.